Hello everyone, am I audible? Please confirm it via chat.
Yes, ma'am, you are audible.
Good afternoon everyone. Welcome to the second session of the day. This will be a practical session and wait a minute. Okay, sorry. Good afternoon, everyone. Welcome to the second session of the day. And this will be a practical session. And for that, I'm very happy to welcome back Dr. Sekhar, a lead computer vision engineer at Samsung R&D. Many of you would have remembered valuable sessions we conducted last week, how to implement transformers. So, with his extensive IT experience spanning over a decade and publications in top conferences such as IJCB, ICTAR, CVPR, and journals like Neurocomputing and Applications, his insights are always enriching. He has also conducted more than 100 plus sessions in IITs, NITs, and triple ITs. So we look forward to learning from him once again. Welcome back, sir. I now request you to kindly take over and start the session. Thank you.
Yeah, thank you, Supriya. So in this session, we discuss about the practical aspects of diffusion models. Okay. So can anyone just revise what actually you discussed in the morning session? Anyone? Yes. So what Juhi Faradi is telling that diffusion models introduce noise and then denoise. So why we need to introduce noise and then denoise? Okay, no problem. So let me just revise for 10 to 20 minutes the how the diffusion model works, and then we look into coding aspects. Okay, so if you see here, so there are we all know that it's of diffusion model contains two steps. One is forward step, and second one is the backward step. Okay, so and what is the ultimate aim is if I give an image, the model has to learn how to regenerate it. So GANs are having one technique, autoencoders are having one technique, VAE, variational autoencoders have one technique. Similarly, the diffusion model. So what diffusion models learn is, so they all start from a clean image, X not the input which we give, and then we add a noise, small noise. So now the image contains both the noise part and the image part. Okay, so slowly we are learning parts of the image, subset of the images. So as I move on, so again, we will increase the noise content now. So image part, noise part. Like this, we keep on adding the noise part. So if you see here, it will be like this. One second. Yes. So it will be like this. So we'll start from clean image. So slowly, gradually, we add noise. So at the end, after various steps, like 1,000 steps, okay, the image becomes totally noise. Okay. So in this process, it will learn the minute details of the image, how to generate. In the reverse process, what we will do, so we will start from the noise, and we'll try to regenerate the image back. So that at every level, we will the model learn the minute details, the hierarchical structures, the spatial structures, everything about the image. This is one of the technique. So you keep on adding the image, and then once it becomes complete noise, where you cannot distinguish what image it represents or does it contains the image or not. From that point, again, we will do the backward process. So slowly we try to eliminate the noise, and then we will get back the image. So this diffusion models got inspired from the physics, where slowly, what is meant by diffusion? In a water, so if you split out oil, so slowly oil will keep on capturing. Okay, so completely it will occupy the water part. So how water spill over the oil spill over the water, slowly it will capture the complete water. So diffuse. Okay, slowly we will also add the noise part. In this process, we'll store various values of the image. We learn various subsets of the image, and finally we will reach the complete image, complete noise. And then from noise again we'll start back. Okay, so we are making the model learn minute details, and we are stressing the model to learn or to remember. Okay, so all subset of the image, and then slowly we'll get it back and we'll try to regenerate the image. Okay, so these are the various steps here. So start from a clean image, gradually add noise at each step by step. So if you add higher noise, so if there is an image, and if you add suddenly jump with very heavy noise, the learning will be minimum. So how to generate this 9? So here itself, without slowly, so you have to add only a small part of the noise, then slowly increase it, slowly. Then at every what is image and what is non-image, the model is keep on learning. So if you suddenly jump to from the original image, okay, like this, then from here to here, it won't understand because only this part is available, only this part. So this part it doesn't learn. So what we want is every slowly, if we make an image to increase the noise, then it will learn first this entire image, then next this entire image. Like this, it will learn, and then we can use it, those subparts, what it learned in the regeneration process. So they're able to generate, okay, multiple digits, multiple nines, because they learn subsets of the 9. Okay, so that is how we are using noise. So it will become pure noise. Then we'll start from pure noise. Gradually, what we have to do is from the noisy image, we try to remove the noise. In the forward process, we will try to add the noise. Okay, adding the noise, subtracting the noise. Okay. Next, after similar steps, same reversal steps, if I do after T steps, I can generate the clean image. Okay. So now, what is the difference between noise here and what is the difference noise here in the reversal process? So we have a noise plays a major role in making the model to learn. So in this process, the epsilon, okay, what is the role in the forward pass and what is its role in the negative pass? Can anyone tell me? What is its role? Any idea? Is the same epsilon in the forward pass and in the negative pass. Is it same or any difference? Anyone? Hmm. Not that difference. The role, the computation, how we compute epsilon in the forward pass, how we compute the epsilon in the backward pass. Okay. Yes. So in forward pass, noise allows to extract the features of the model. Very good. Okay, let's see. Let's go further. So we always starts with a clean image. Okay. So always starts with a clean image, clean and original image. Okay. Next, all diffusion models start from a real clean data. So what we need to do is we need to add a noise factor. So define noise schedule. So you have to compute the beta. Beta is a noise. Okay. So as you have to add the noise in smaller steps, you have to define the range. It should not be very less. If very less is fine, but it should not be very high. So if you add the basic image x naught plus 0.5, it will become very tough to learn as noise factor is very high. So it should be stable. So slowly it has to change. There shouldn't be any sudden jump. Okay. So you have to define the range. At each step t, we are going to add a noise. So what is that noise? I'm defining beta at each time step, beta 1, beta 2. So t, we will pick up a number, we will add. So now there will be two components in the total image. Okay. So beta is the noise, x naught, or we can say 1. So x naught is what my original image. What we are doing, we are keep on adding the noise. So now what happens? Image part and the noise part. So from the image part, okay, so if I remove the noise part, total image. So this is the alpha t. What alpha t represents? So what is the image? How much image is left and how much noise we added? Okay, so these are very important terms, beta t and alpha t. So alpha t is the image part, the part of the image which is visible, and 1 is the total image we are assuming, and beta t is the noise factor. So total minus the noise factor results into the image part. So like this, image 1. So we are naming it as x01. So what we try to compute, see here, this this is what we are doing. For each image x01, we will choose some random, see time. Suppose if you fix it time, say 1 to 300 time steps if you want to use. Okay, so x01, 2, okay, 3, like this, we have 300 steps. So what we want is that every time we choose a random t, say 600, sorry, say 60. So for this x01, we will set time to 60, and we will make the model to learn alpha 60. This is alpha hat. So at any particular time, what is the noise component? And if I subtract the noise component, we will get the alpha 60. So see here, clean image. This is the time we are going to compute alphas. So what is t here? These are randomly chosen time steps for each image. So we decided how many epochs. So we can say one, which is the epoch. Instead of using the timestamp, times a timestamp for every sample. So what we want is we will change it. You can do same also, no problem. So you want the model to learn how to denoise images at all possible noise levels. Okay. So various levels we will use, and based upon this, we will generate alphas. Okay. Suppose if we decided for image 100 time step 150, 200, 250, then if you see here, we are going to compute alpha t. So see here how we are going to compute alpha t. This is the key. For each image, you need to compute how much original image is still preserved after timestamp t. So how we will come to know? You do this by looking corresponding value to alpha hat array. You no need to worry. So I just want to introduce the formula. So this is the main formula. So how we arrive this formula? Okay. So each term we try to understand. Okay. So the entire forward process depends upon this formula, which is equal to, which is called as a closed formula. What it means? From any image, you take any image. This is the base image, which I'm calling it as a X naught.
Excuse me, sir.
Hello?
Hello.
Excuse me?
Sir, your screen is not visible
Oh, sorry.
if you are sharing the phone. Sir.
Okay. So, okay. So, I want to see. This is the forward pass formula. At any time t, how this is the base image. This is the base image. And that base image, at time t equal to 0, at time t equal to 1, t equal to 2, t equal to 3, like that, we will decide how many total time steps. So those time steps, how it look like, we must be able to compute. So if we reach the last time value, it should be completely noise. So initially it is image, okay? More image, less noise. So second step, assume that there will be 2 rows of noise. Third step, 3 rows of noise. Okay, like this, slowly it will, like this, it will. So at the end, it will full noise. Starting, it will be full image. So this formula helps us rather than repeatedly computing at each level. If I give X naught, the base image, whichever timestamp you want, 0, 1, 2, 3, whatever may be the timestamp you want, you just specify by using these alpha values and this epsilon, I can able to compute xt. So computing xt is not a problem. Suppose if I want to compute x100, the image after 100th time, where we keep on applying the random noise, which is equal to square root of alpha hat t into x naught. So x naught is the my ground truth, my original image, plus square root of 1 minus alpha cap t into noise. So this is the noise part. This is the image part. So x naught is my starting image. Epsilon is the noise. So for an image, I need to compute alpha t. So if I have an alpha t and corresponding noise, so for any transition, I need to compute alpha t, comma, epsilon. So this plays a major role. So what is alpha t? So we need to understand what is alpha t. So if I know alpha t, then I can plug in here for an image. for an image, what is alpha t? So there is an image, x naught. So for every images, say I1, okay, starting is x naught because there is the assumption. So I2. So starting, I'm calling it as a x naught. So for every image, I need to compute two things. One is the corresponding alpha t and the epsilon. Okay. So how to compute? If I know alpha 0, alpha 1, okay. So till the last timestamp, alpha t. So for any image, so for I naught, I need to compute this plus the epsilon. Next for I1 also, its corresponding alpha naught, alpha 1, alpha t, comma epsilon. So for every image which is in the training data set, I need to compute these values. So how to compute this? So for an image, there will be n number of alpha t values. For each time step, you are computing. Okay. So x naught is the original image, and epsilon is your randomly picking up from a normal distribution with 0 mean and 1 variance. Somewhere you will pick up the epsilon. And what is xt? The noisy version of the t steps. Okay. So how you will compute? So alpha 1, what is alpha 1? Alpha 1 equal to 1 minus beta 1. Okay. So beta 1, we are starting with very small values. So what is the range of those values? The allowed range, okay, 0.0001 small values to some higher value, 0.02. So the inducing the randomness, the noise into the image happens very slowly. It depends upon what beta value you have chosen at time. Okay. So this is the beta value you can choose from that range, very small range, 0.004, comma 0.02. So in that range you can take, and you substitute from 1 minus beta 1, use alpha 1. Similarly, alpha, second noise level, second timestamp level, x2 I want, which is equal to square root of alpha hat 2. So alpha hat 2, you will compute alpha 1 into alpha 2, which is equal to 1 minus beta 1 into 1 minus beta 2. So it all depends upon the beta values. So alpha 3, you have to multiply with 3 beta values. Okay. But why you are using alpha hat, it's okay. But why you are using alpha root here? So the square root ensures that both clean image and the noise. So this is the clean image, and the noise contribute the right amount of variability into final noise image. The variations. So what is the image you have? The image portion and the noise portion must be same variance. So that's why we have to use square root. So no need to go. Okay. So this is the formula. Now, can anyone tell me, suppose if I try to generate xt, which is equal to square root of alpha t into xt minus 1 plus square root of 1 minus alpha t cap into epsilon. So if I use xt minus 1, if I change the formula from x naught to xt minus 1, is it simple or is it complex? So why can't we take the previous image, add the noise, and then get the next image? And for that next image, do the formula, get the next image. So why can't we proceed like this? So why we are using x naught, starting from x naught? Which one is efficient and which one is complex? Yes, Ramesh, you are correct. So now tell me my question. So why can't I frame a formula xt minus 1 from where I will get xt? Okay, from xt, I can get xt plus 1. So from the previous step, I can get next step. But why we are starting from x naught? Can anyone answer this? So Abdul is correct, because we need to store from 0 to all the timestamps. Like suppose if I have t timestamps, I need to store x naught, I need to store x1, x2, x3, all those values. If I compute, if the formula is based upon the previous values, correct? So what we did, instead of starting from xt minus 1, so if I want to generate x1, I need x naught. So if I want to generate x2, I need x1, right? So every generation requires all the previous images, which is very tough to store. This is only for one image. So we may have multiple images. So that's why every image, I'm just store x naught, but I will try to compute these alpha values. Those alpha values will give me what is the noise part. So what is the image part? What is the noise part? So that is how, instead of storing all the previous versions, I can just compute based upon x naught only. So if I know the clean image, at every time t, what will be my image part, what will be my noise part, I can easily compute. So this is my noise. This is a factor, weightage. This is my image. This is the weightage. So from the image, okay, at every time step t, for an image, how much I need to compute. The remaining, I will compute for the noise. Okay, so that's why if I know x naught, so if I store alpha t, if I can able to compute alpha t's, it is better, optimal compared to store all the previous versions. Okay, so that's why this is called as a closed form formula. Now the importance is alpha t. So what alpha t indicates? Weight. It's also a weight. So if this is an image, this is a noise. So it indicates the weight I need to consider for the noise. The remaining part I will consider for the noise. So alpha t plays a major role. So you need to compute alpha. So how to compute alpha? How many timestamp you want? Suppose if for one timestamp, we have first timestamp, we have alpha 1. Two timestamps, see here, the formula is like this. This is the formula. Okay, so product, if I say alpha equal to 1, it is alpha 1 only. 2 means 1 to 2 product. So alpha 1 into alpha 2. Suppose t equal to 3 times steps. Okay, then alpha 1 into alpha 2 into alpha 3. So this is how we are going to compute alpha t cap. So what is alpha? Alpha equal to 1 minus beta. So for 1 minus beta. What is beta? Beta is what? A constant which you are slowly you are adding from a small set of values. Okay. So the entire operation is what? The beta value. How you are adding the noise. So the entire forward process add noise gradually. At each time step t, you add a tiny bit of noise, beta. Typically we will choose the noise values from these set of values. This gives alpha t equal to 1 minus beta t. So alpha tells how much of the image we keep at each step. This is the image part. This is the noise part. Okay. So this is what the noise, you can take a number from this and then add it to the pixel values. Okay. So now if I take any image, this is the clean image. Okay. And then for an image, I want to compute at time step 100, t equal to 100, how my alpha look like. Okay. So this one, this is alpha cap, alpha cap. So how alpha cap and alpha are related? By using this formula. So product initially alpha 1 equal to, okay, alpha 1 cap equal to alpha 1. Next, what happens? For any time, as time step increases, the product increases and alpha equal to 1 minus beta. So alpha t cap equal to product phi 1 minus beta s. So beta is a random number which you are choosing. So we will create a noisy version x100, meaning the version x01 corrupted by 1000 steps of noise. So after 1000 steps of noise, how x01 will look like? For that, I need alpha, corresponding alpha. So how this alpha is computed? So alpha is computed, this one, s equal to, so I need to compute alpha 1, alpha 2, alpha 3, alpha 4, alpha 100, and then I need to take the product. So which is equal to 1 minus some random number between that range into like this. You will do it for 100 times. You will get a number. That number, you will add it to the image. Okay. So see here. So that alpha you are going to compute, okay, by using this formula. So suppose if I want to compute for x100, so I want to compute x100, how it look like? So x01 is the clean image. If I transform it after, if I keep on adding the noise, at x100, how it look like? So if I want to compute x100 out of x01, okay, so I need to compute this value, which is equal to 1 minus beta of s. What is beta of s? Some random number between this value. So you have to do 100 multiplications with random number. So 1 minus select the number into 1 minus select the number. So like that, you will compute for 100 values, and those values you will put it here. And as I said, this will helps us to keep control of the noise part and the variance part. That's it. So epsilon for each image, there will be an epsilon. See, image 1 associated random number, image 2 random number, image 3 random number. So each image must have its own alpha t and its own epsilon. So these two values plays a major role. And alpha comes from the beta, which is a random selection from a specified interval. Second thing, noise. Noise comes from the Gaussian distribution. So by using this, we can able to generate any t type timestamp t image. Clear? That's it. So what is beta t? Beta t controls how much noise we add at each time step t. So it's called the variance schedule. So if higher the beta, the more noise you are adding. Okay. See here, we have to use very small beta values. So why we have to use very small beta values? The learning, the entire idea of diffusion, see how oil will spill over the water. It moves very slowly. So is to add noise slowly and smoothly, so model can learn to reverse it step by step. So how to move? See, if I do a small change, if I do a small noise addition, it will be very easy for the model to learn. Okay, it will be very easy for the model to learn. Or suppose if I transform into like this, then it won't understand. So slowly and smoothly we have to do. That's why we have to choose small set of values, typically in this range. So we will have many smaller steps. So it will be more number of steps to reach to the noise. So if there's a sudden jump, model will miss these learnings. Smooth degradation from clean image to pure noise is required. Stability during training. Okay, so what tiny beta will do? Gentle correction of image. Okay, results into smoother learning. And if you use larger beta t, the model tough to learn. So ultimately, what is alpha cap? Alpha t cap equal to product of all alphas, which is equal to product of 1 minus betas. So alpha t cap tells us how much of the original image is still preserved after t time steps. How much image is left? That is what taken care by alpha t. So what happens in forward pass? So in forward pass, adding noise is simple, which is fully mathematical. So you are taking from beta and some epsilon, you are adding. But in reverse process, what we need, you have a noisy image. I have a noisy image, but if I have a noisy image, see, if there is an image, adding epsilon is not a problem. You choose some random number and you will make it corrupt. But if you have a corrupt image, getting that epsilon is a problem. So how to solve this? Can anyone tell me? How to solve? What is the major step? What is the major step in the reverse process? Reverse process. In the forward pass, epsilon is simple. I will get it from a random number from distribution. And here in the reverse process, how to estimate the noise present in an image. If we know that, that's it. It is done. Can anyone tell me? So if you see here, see, so you don't know, see, you have noisy image xt, you don't know exactly what the clean image x naught was. So you don't know exactly what noise was added. Because we don't know x naught, if I have x100 with me or xt with me, I cannot see, just if someone gives me the xt image, I cannot say what is the noise content because I don't have access to the ground truth. So, but I need epsilon. Why I need epsilon? Because xt, I need to subtract epsilon. Then again, I need to subtract the random quotient. The random values I need to keep on removing so that I will get my original image. So that's why we train a model. So when I pass, we need a model. So what that model will do, so when I pass an image, so xt is an image and at a time step t. So this is the image. So I will say that this image is generated from original image, but I don't tell the original image, but I will say that this is the xt image. That is, it represents the noise version of the image at a tth time. So if I give the image and I say it is 100th type, 100th time noise image, then we can predict the noise. So if I predict the noise, I can subtract it slowly and we can reconstruct the image. So what I will do for every image, see, what is learning here? For every image, the noise portion will be there. So for every image, there is a noise portion. So this is xt. At time t is a transformation from x naught, where there will be a noise component also. So if you train a model, so in such a way that, okay, so each image x naught, for an image x naught, you are training the epsilon, okay, by using a model, and then you will get back that epsilon here. So there is a model, it learns the parameters, it will give you the epsilon. If I pass xt, comma t, I can get the epsilon. So if I keep on subtracting that noise component, I can get my original image back. So that is what happens in the reverse process. In the forward process, it's straightforward, adding noise. What is a backward process? You have to subtract noise. For that, you need what is noise. In the forward process, yes, there will be a distribution. From that distribution, you will get the epsilon and you will add it. But in the reverse side, reversal process, no one will tell you what is the epsilon. So you take a model help, you will get the image. Okay. So with this theory, okay, so hope this theory is useful because I just want to add some theory. Now let's go to the coding part. So any doubts here? Any doubts? Yes. In any way, in both the process, it's a random number. You have to pick it from very small range of interval. Okay. So let me explain the code. Okay. So let me explain the code. Simple. I added the comments for easy understanding. So TensorFlow based code. We need a base data set. So I'm taking MNIST data set, which is pre-existing. From the predefined MNIST data set, I'm using Xtrain. I'm not interested, like it's unsupervised. The generation is unsupervised. So I don't want white train. And we are not testing. So all these samples we least bother. So I got Xtrain, my main train data set. And what I'm doing is, so initially the pixel values is 0 to 255. So I'm using -1, 1. So I'm normalizing. Okay. So any learning like GAN, VAE. So if you make it to range of -1 to 1, so see here, diffusion models learn better in this scale rather than this scale. Okay. Adding -1 channel dimension. Okay. I'm expanding my dimensions at -1 from the bottom, from the last. So, and this will be added. So it will make three-dimensional, which I can feed it to input. Batch size. And then by using tensor slices, I created the data set. So I downloaded the data set. So this is what we studied. Forward diffusion. So forward diffusion means adding noise, which is equal to 1 minus beta t. So beta t is a small noise added at each step. So what alpha t represents, how much of the image is kept at step t. So if you subtract noise, you have the image. How much is left? 1 minus beta t. So how much imageness is present in the image? So see here. So we want to know how much of the original image is still preserved after multiple steps. So alpha hat 1 equal to alpha 1 only. What about alpha hat 2? You have to multiply 2 alphas. 3 alphas. So we will store in tensor. So you can pick it up and multiply. What is alpha hat? After t steps, we are computing square root of alpha hat. Fraction of original image is still present. And what is meant by 1 minus alpha hat t? This is the accumulated noise. Accumulated image, accumulated noise. So that is what we are using here in the just now I explained. Okay, so I'm unable. So here, so this is the formula, right? Okay. So alpha t into x naught 1 minus alpha t into epsilon. So that is what we are doing here. Okay. So 1 minus square root of alpha hat t we are computing, and then 1 minus alpha hat t. Okay. Okay. So 1 minus alpha hat t and alpha hat t, we are computing the square root. Okay. So that is what we are doing here. So how many steps you are using? Total 300 steps I'm using. That means total diffusion steps. So we are adding noise. So the conversion, the initial image from the initial image to the last part. So what you are using is, you are using almost 300 steps for transition. So 0 to 1, 2, 3, 4, 5. So see, you are not suddenly making it like 10 steps. So you are taking 300 steps. That means almost 300 times you are adding noise slowly, in small quantity to make the complete noise. So that you are making the model to learn minute details. So how much is noise and image. So it will learn this part. Then again, this total will be noise. This will be the image. So whatever image part is left, it will learn thoroughly. Okay, that is simple text. Okay, next, see here. So you are picking up the numbers from 0.004 to 0.02. So beta controls how much noise is added at each step. And alpha is 1 minus beta. So beta controls how much noise is added at each step. And this is alpha. So alpha hat is see here, cumulative product. So multiply together all the alpha values from time step 1 to time step 2. Alpha hat. Alpha hat helps track how much clean image remains after each step. Okay. So that is what is cumulative product. Cumulative product we just see here. Cumulative products. Suppose if we want it from S1 to S2, which is equal to this one. Only S1, this one. So this is cumulative products. It all depends upon at what time you need. If you want for time t, you have to do it for 3 times. Okay, that's why I explained, which will make the code easier. Okay, and then you are coming here. The function simulates the forward diffusion process. So you are giving the start image. So it adds small amounts of noise depending upon timestamp t. So over 300 steps, you are converting a clean image into random noise. And then this is how we create noisy training data for the model to learn from. So extract noise equal to none. So you have to add a noise. So you can specify. Okay. So how to generate the noise? Else randomly it will generate. So this one. So what? See, we are computing square root of alpha hat t equal to gather tf dot square. See this one, square root of alpha hat t. So I explained here what is meant by gather. So somewhere I explained what is gather. Okay. Next, see tf gather dot square root of 1 minus alpha hat. This is for the noise. Okay. So same thing. How you are this formula all about computing the values till here. Okay. So gather means how many products. Because at time t, what happens at time t? So it has to compute. What gather will do? It has to compute those many alpha hats. So that's what I explained here. So what will happen? So when I say gather 100, I'm passing the base image plus 100. So what it tells at 100th time, how your image will going to be. So that is what happens here. The gather will say, see, you are passing time, tf dot gather, you are passing time t. See here, every time we train, we want different random noise added. So the model seems many noisy versions. Okay. So that is what square root of alpha hat t. So how to compute square root of alpha at t, this value equal to, so first you have to gather and then you have to compute the square root. How to gather means you have to perform the cumulative product. So this formula we applied here. Okay. So this is adjustment, the reshaping. So two things here, square root of alpha hat t. Okay. Next, into extract this formula. Finally, you are doing this this one. So x naught extract into square root of alpha ht. So how you got alpha ht? Same process. If you want to compute this, I explained here. First, you have to compute alpha t. For that, you have to compute alphas. You have to take the product, and then you have to take this, which is equal to this one. So, if I want to compute alpha t, I have to gather these values. So that is what happened here. It will take care alpha hat. If you say this one, tf dot gather square root of alpha hat t. Okay. So by using this, you will compute square root of alpha hat t into my original image, and then you are computing square root of 1 minus alpha ht into the noise part. So this is the noise part. So this is the noise part into square root of 1 minus alpha t plus x naught into this one. So xt into square root of alpha hat t, noise into square root of 1 minus alpha ht. So this is the, whatever image you pass, you repeatedly, you can compute the values. See, there is nothing, Abdul, there is no difference between the image or a tensor. How you will represent an image? Mathematically, it's a tensor, RGB. Okay. There is nothing like image encoding. It is a tensor. Okay. So this is the formula. Okay. Next. So we need a unit. So unit has to learn. So as I said in the reverse process, here, definitely we need help from the model. Somewhere I explained. So why we need the model? So while forward process, it can get the value, but in the reverse process, if I want to know, see here. So I need model. So this is simply unit model. Okay. So unit model, so I explained everything, like the input shape which you are going to pass, and see here. This is the noisy image that the model will receive as input at each diffusion step. It will receive. Okay. So see here, time step input layer. Each sample also receives its corresponding time step. So it receives two things. Okay. Somewhere I explained about the model. Two things it will receive. One is the image and the timestamp. So what it will generate? It will generate the noise. I don't know where it got missed. Okay. So as I explained, it will take an image, clean image, say X start, comma, teeth time. And then it will give the noise. So this is what happens. Okay. So simple, see here, that particular, so what we are doing is, we are mixing the image and the timestamp t as a channel. Okay. So the timestamp, the number, okay, the number, say suppose 32, whatever may be the timestamp. Okay. The timestamp is the timestamp, say any number. Suppose I want at 16th timestamp, I'm representing this 16 as a embedding vector, time embedded vector. And this embedding vector, I will convert into the size of the image. So this is the original image. I will concat this as a channel. So it will become 2 channel. So that is what happens here. See, I got time embeddings. So embedding layer for timestamp, whatever timestamp you pass, for that timestamp, I'm computing the embeddings. And then see, I'm reshaping the embedding into 2021. Then I'm concatenating the image and the corresponding embeddings. And that is what I'm going to pass through the convolution layers. So the each pixel value represents the image value plus timestamp information, both is attached and that pass through the convolution layers. So convolution layers learns, see here, nonlinearity, all these things like features, okay, and complex patterns, hierarchical features. So all those things it will learn. Okay, so inputs, return, it will input like, see here, the final output layer, one filter map back to a single channel image, same as input it will generate. Okay, so that is what happens in the simple UNet model. So it will take a random number, okay, input layer, finally it will try to generate the image. Okay, so train step. So what happens in the train step? Same thing, generate the random number and then see xt noise q sample. So we are calling this function q sample. So q sample will generate the image. What it gives the x start, it gives the timestamp. Okay, so see here, this is a training step. Okay, so it what it will do is it is calling this function. So x is the input it received. See, t is the time randomly. Okay, so randomly we are generating the time and we are passing the time. What noise to add it? In this noise, if I apply t times on this image, how it look like? That is what the Q sample is going to generate. That is xt. And now see, we are passing that. Once I got the xt image, we are training the model. So see here, see model. I see this is the model. Get model. So we got the model, right? So get model is done. I have the model ready with me. So what I'm doing here, model, I am passing the image at tth time and the time t. Okay, it has to get the noise, predict the noise. And I'm just checking what is my original noise that I added in this image. X time t, the original image, time t, the noise I added, I got xt. Now that xt, if I tell time t, my model has to predict correct noise. So that I'm using mean square error to reduce the difference between the original noise added into the image and the predicted noise. That is what the loss. So this is how I'm using the train step. So train step uses generation of the forward images, and those images I use to train my model. So okay, so now what I'm doing, epochs equal to 10. So in 10 epochs, okay, so I'm taking the train data set. So where I generated the train data set? So train data set is what the MNIST data set I received. So this is MNIST data set. I got the extrained data, and extrained data I added the channel number, added the channel, and by using the TensorFlow, by using batches, I made a batches of data set. So that is what my train data set available. Next, what I did, whenever I get any image, specifically it's a start image, and if I say the time t, and I will generate how this start will look after t times when I add a noise. So that is what this formula. So that is the image. Now I need to train. So what I will do, I will generate the batches. So train step of that batch. So that batch I will use, and then I call the train step. So I will go to train step. What will happen in this train step? I will generate the time t. For each image, I will generate any random t, and I want my model to learn. See here. So for every image, randomly I will select one time t. So for x0, how it look like after 100 iteration. X0 to how it look like 150 iteration. That's what I need to learn. So see here, for every image, the random t I will select. And the noise. So if you have your own normal, it's okay. Else the model uses the default. The model uses the default noise, random noise. That's it. So you will train the model. So what the model got trained? My model got trained. Can anyone tell me what my model got trained? On what my model got trained? Can anyone tell me? When I say training is done, what my model got trained? Very good. On predicting loss. The loss is on, what is the loss between? The loss between the noise. Very good. The noise means the original noise we added and the predicted noise by the model. So what we are doing is we are making the model to learn how to generate the like this, not sequentially. See here. So this is how we are training X2 image. One second. Okay, randomly teach time, not sequentially. At any timestamp, any image, how it look like. Okay, after teach timestamp. See here, X02, I want my model to learn how it look like 150. X03, how it look like after 200 timestamps. Okay, so these are randomly chosen timestamps for each image that we use to train. Instead of using the same timestamp for every sample, we are using different timestamps. So that makes my model to learn all possible noise levels. Okay, so this is how I'm training. I'm randomly selecting a timestamp T. Okay, and then I'm passing the original image and noise. I got the noise image. And now that is what I'm passing to my model, xt comma t. I want my model to predict the noise. That's what the predicted noise. This is what the original noise. I want to compute the loss. That is how my model will train. Once my model trains, then that's it. I can generate. Okay. So see here, this is just once my model, this one. So what I'm doing is, see here, I want the the forward process. Okay. So from X train, okay. So we are choosing samples, and then what we are doing is, see here, we are calling Q sample and the timestamp T, how it look like. So fourth timestamp like this, various timestamp 0, remainder divided by 4 like this, and I am passing the timestamp. I'm getting the noise images, and those noise images I just displayed at various timestamps. So how I'm able to generate? By using Q sample. So in this process, there is no model. Model is not required. So it goes to Q sample. It goes to Q sample. Model is there. Image is there. Time T is there. So noise is also there. So just we will apply. So that gather at a 100th time, I need to get at 100th time what is my value. So for that, I need to apply this formula. So sequential product, cumulative product. Cumulative product I need to apply. Like that, for 4 images, these products I need to compute for 4. So if it is 100, so 1 to 100 for first image, 1 to 150 for second image, 1 to 200 for second, third image, 1 to 250 for fourth image. Like this, you need to compute those xt values for each image. That's all happens with the help of gather. Okay. And now this is samples we have seen. And now the backward process, the reverse denoising. So reverse denoising, very simple, because I have a model. Okay. So you just have to generate any sample you generate, and then you pass the images. So you are passing the images, and then see here what it requires, the model. So model requires image and timestamp too. So you are generating the model here, model timestamp, and then it will predict the noise. And then you are computing, see, alpha t, alpha hat t. So you are getting it from, see, alpha hat t. You compute those values. Somewhere it's available. Okay. So see here, alpha hat t. So we have that alpha hat t tensors, like with indexed values. So we can pick it up. Okay, so somewhere it will be alpha hat t. See, cumulative product. So cumulative products. Okay, so at each timestamp, this alpha hat will have values. So for that particular image, okay, so for that particular image, for that timestamp, you are getting alpha t, you are getting alpha hat t, you are getting the beta values, and then you are applying the formula. Okay, so 1 by square root of alpha t, so 1 minus alpha t. So this is the formula you are applying coefficient 1 and coefficient 2. So that is what you are trying to generate the images. Okay, so these are the denoising. Main thing here is the model. So model will predict the noise for you, prediction noise. And this alpha values contains the alpha, because you need alpha hat, right? So alpha hat and these values are already in the forward process we stored. So don't need to compute. So we are getting those values, we are retrieving those values, and then we are trying to formulate the images. Okay. So and then we can generate sample of the model. So you can just call this one and you can try to generate those samples. That's it. And those images you can display. If you see here, see, I'm just using this as a, for every t in the range of t, see, I need to come from reverse it, right? So this underscore, you can just remove it, but no issues. So I have t value. So, but reverse what I need to do, I need to start it from, I just reversed it. So t to 0, not 0 to t, you have to start from t to 0. So this is just a notation. Okay. So for that timestamp, I need, so if I want to generate for any timestamp, same formula will apply. Okay. So only thing is, see, for the entire generation, see, if you want to generate, you just need alpha t and 1 minus alpha t. So these values are stored. So that is what alpha t, alpha hat t. So these are stored in the tensors. We are just retrieving them. And then we are just computing the values this side. So this is the forward pass. And now you have to compute the x naught. Okay. So how you compute the x naught? If you have xt, this is the formula. You have to reverse it. 1 by square root of alpha t, this one. So if you apply this formula, you will get the original image. What you are doing with the forward pass? So in the forward pass, you are doing this formula. Where is this? This one. So if you know the noise, if I know the start, I compute these values. Now what happens? I know this is a reverse part. So this is the reverse image. See, this is the image. Okay. So on computing these values, so you have to get xt minus x naught. Okay. So what is epsilon? Okay. What is x naught? So this you have to compute. Okay. So if noise is present and one this like this xt minus this value divided by square root of alpha t cap xt minus this value 1 minus alpha t into epsilon. So 1 minus alpha t cap into epsilon, that will gives my original image. So if I give xt, I retrieve these values from the tensor, then I will apply this formula. I will predict the noise from the model unit based application. So if I pass xt and the timestamp t, I will get the epsilon. So that epsilon I will put it here. And for the timestamp t in the storage, I have these values. So I will club into this formula. I will get this image. Okay. So that is what, see, 1 by square root of this one. That is this one, 1 minus alpha t. So 1 minus alpha t. Okay. Divided by np square root of 1 minus this alpha hat. So into this noise. So this is how we get the image. Okay. So this is how the forward pass and the diffusion. Okay. So if I run this, I just added comments. Okay, so this cumulative product will do this cumulative products. For every T, it will compute. Okay. So we can pass xt for T, then it will compute the values. This is the model which will give us the noise epsilon. And we are training with the MSC loss. This is the function. So this train function will use to whatever may be the base image at every timestamp, random it will pick up and it will try to make the model to learn. So 10 times we are training. So if we train more number of times, we may get better results. But okay, for demo purpose, I'm just training it for 10 times. So I will share the code. You just play with it, increase the size, epoch size. Okay, then we can make the model efficiently denoise the data. So randomly chosen 4, slowly it will add the noise. Okay. And at the end, if you see, it is completely noise. And now reverse sampling, reverse diffusion. See, because of this model, the complexity became simple. But if this model is not used, we have to use advanced mathematics like constant optimization. So all those things we have to use. So training is less, so it enabled to learn. But if you make more number of iterations, so it will be able to pick it up correct images. Okay, so you try with more images. Any doubt? So two important functions. While forward Q sample, which will take the image on the timestamp, and then it will try to gather and cumulative, it will use the cumulative product to compute the images. And in the denoising process, because of that model, it became very simple. So we are training the model with the noise. What is the noise in the present in the image? Okay, so we want the model to predict. So in denoising, we will give that image as an input to that model. It will give the noise, and that noise I'm applying in the formula. So that QNet model is making the task simpler. So by giving the model the image, the images and the t values. Okay, so it is predicting. So this simple steps reducing a lot of complexity. Else we might have to apply deeper mathematics to predict the noise. But the model is helping us. Once you get the noise, you apply this formula, you will get the image back. Okay. Any doubts? So can anyone just list the number of steps in the training process? What are the number of steps in the training process? So how you will train? Q sample. Image with respect to T, it will vary. Okay. And in case of denoising, the model is ready. Okay. So forward pass is just computation. So there is nothing training involved. Whereas in case of the backward process, you making the model ready. So forward pass, that forward pass images you are using in the model training, you are making the model ready. Whenever you need help, you are passing the xt comma t value to the model, you are getting the noise. Based upon the noise, you are able to generate the image back. So any doubts? Okay, so if there are no doubts, we can stop it here.
So, sir, should we wrap the session?
Yes.
Okay. Thank you so much, sir, for sharing your valuable knowledge with us. And we really enjoyed today's session. It was truly an enriching. Thank you so much.
Thank you. Thank you.
Thank
Thank you.